Welcome to this module. We'll look at what linked lists are, and we'll see how structures can be used to represent linked lists. So we have seen how structures are defined. There is one important class or use for structures, and we'll see how to do what is called self-referential storage. This is a very useful thing to do, and this is also something that you're going to learn in a lot of detail when you do what are called data structures. So I want to do this in C a little bit, and also use the example here to motivate the need for C++. So the reason why we are using C++ in the following lectures on data structures is that the syntax becomes much simpler and cleaner. Even though your course is based on C programming, there are a few lectures that are done using C++, and it's good for you to know the syntax of C++ so that you can appreciate what is happening in those lectures. So let's start with the list. List is nothing but a collection of items. So maybe I have a lot of books at home and I want to maintain a list of books on my shelf, or I teach a class and I want a list of students in my class, or even for a particular student I want to track all the list of marks in that particular semester and so on. So clearly you can implement this using arrays, and one small issue with the arrays is that every time there is a change in the number of items that you need, you either have to shrink the array or expand the array. So C does not give you a nice feature to either expand or shrink arrays. So if you say array int a of 100, you have 100 integers and nothing more, right? So this is a small problem. Maybe I have only 90 students in my class, but I allocated space for 100, right? Or worse, I have 110 students in my class and I have space only for 100 elements. It would be nice to be able to expand or shrink based on the necessity, and one basic way of doing that is using what is called a linked list. So let's see how a linked list can be implemented. So usually what you have is you have the notion of what is called the data. The data is what you want to really maintain, but you define a node, a structure called node, which has the data that you want. It also has something called next. Okay? So such a structure would look like this. You have struct node and you have, let's say, double data node star next. So what we are going to do is we are going to use this field called data to store the data that we want, and we are going to have this field called next, which is going to point to the next node. So you can see that there is struct node here and node star here. This is what makes it self-referential. So you are having one element of the type whatever we want. In this case it's double, and we are going to point to the next element which is of the same type and so on. So you can think of this as playing treasure hunt. So you start with one location where there is a clue, and this gives you a pointer to somewhere else where there is a new clue, and you keep chasing the clues till you go to the end where you have a prize. So this is how this game called treasure hunt works. You can think of a linked list in a very similar way. You have data instead of clues, and you also have clue which tells you where to go next, and then you go there, you have another clue and so on. You have a chain of these things. At some point this list ends. So I already mentioned self-referentiality comes from the fact that you are referring to a node of the same type, and here if you notice we have struct node here. This node is immediately visible here. The data type called node is immediately visible here. That's not a problem. C allows you to do that, and C has this feature specifically because it wants to support the self-referential structures. So now let's say I have three nodes, namely A, B and C, let's say, and let's say that node A is supposed to have value 12, node B is supposed to have value 17, and node C is supposed to have value 14. Okay? And we have data and what are called the pointers. What we are going to do is we are going to chain them together. From A we link its next to B, from B we link its next to C, and C is not, so C is the last node in the list, and we don't want it to point to anything, so we need to have some null at the end. So now we can see that this is a linked list. So it's a list, but to reach one element you have to start from the first element, follow the links that point to the next element and so on, and keep going and till the end. So if you want to reach 17, you cannot access 17 directly. So in an array I would have accessed a of 1, that would have taken me to the second element in the array, a of 2 would have taken me to the third element in the array and so on. However, in a linked list you access the first element, you chase the pointer here and get the next element, then chase its pointer to the next element and get to the element after that, and so on. So we assume that A, B, C are all pointers here. Therefore, if you do star A, it gives you this structure, and you can do a dot next equals B. So remember, B is a pointer, so A's next field is also a pointer, so these are compatible. Finally, for null, I already mentioned that there is a keyword called null in C. So star C dot next is null, which means C has nothing following it. So if you are using some operation, if you are going through the list one after the other, once you see null, you are at the end of the list, you cannot go any further. There is another way to do the same thing. Instead of star A dot next, you can also do A arrow next equals B and so on. We already saw this as pointers to structures, and we saw the arrow operator earlier. So now if I ask you what is A's next, so what is next to A, then you start with A, you take next, you go here, you have one more next that goes here. So A next to next is actually the pointer to this node called C here. So whatever C is pointing to, that's the pointer you will get. Let's see how this, so all this looks abstract, right? I have a list and so on. Let's see how this looks in memory. So we want this abstract list, we want node 12 linking to node 17, and node containing 17 should link to node containing 14, and node containing 14 should not point to anything more. This is what we want, and these nodes could be in different locations in memory. For instance, maybe node containing 12 is at location 600, node containing 17 is at location 800, and node containing 14 is at location 112 and so on. And if you establish the linked list finally, this is how it must look like. So you will have 12 at location 600, and the next field contains the address of the node containing 17, and what is that address? It's 800. So that's what we have here. And if you go and look at node containing 17, that's at location 800. What is its next value? We want it to point to the node containing 14, so that's at location 712, and that's what we have here in the address and so on. So in the memory this would look like this, and as an abstract way it is what you see here. So 12's next is 800, and which means if you go to location 800 you get the value comma next pointer. If you go to location 712 you get the value and next pointer, and null is nothing other than 0. So null is defined to be 0 in C, and this is a fairly simple and straightforward way of using a structure to make a linked list. So there are several operations that happen on a linked list. You may insert a node, you may delete a node, you can find a node or display the nodes and so on, and this is a very basic set of operations that you do. Let's say I have 100 students to start with and another 50 students signed up for the course. I go and insert 50 more nodes and have them in order. Maybe some student drops out of my class, I want to delete that node, or I want to find a student who has a particular roll number, I may have to search through the list and find it and so on. So the notion of linked list allows me to do all these things one after the other. Let's see how insertion of a node might be implemented. Let's say I already have a list where I have nodes containing 12 and and the node containing 14. I have two nodes, and maybe there is a list that's following that. I want to insert this node containing 17 between 12 and 14. Let's say I want to do that. You have to do a series of pointer manipulations. What you really want to do is you have a new node which contains the value 17, and since you want it between 12 and 14, you want this node's next pointer to be 14, right? So how do you do that? If this node is B, B's next should be A's next. That's what we have here. So B's next is A's next. Now this does not form a linked list, so it's not a chain of nodes that we have now. Instead, we have two nodes pointing to 14. There is no way in which you can reach this node containing 17 from the node containing 12. We need to change that, and the way to do that is if you make A's next point to B, then A's next field pointed to B now. Now if I start from A, so A's value is 12 and A's next will point me to B, B's value is 17 and B's next will point me to 14, and so on. So now you have a linked list and you have one element linking to another, and so on. And if I want to insert at the beginning of the list, let's say I have struct node star my list, that's the pointer to the whole linked list, and I want to insert a node at the beginning of the list, then the sequence of operations would look like this. So I created a new node, I will take that and point to the first node that is already in the list, and I should change my list to point to the new node. So in this case I am not showing what the contents of the new node are, but that's not the point I want to make here. I have inserted a node, and if it had some valid value, let's say D, and if I go through the list, if I traverse the list from the beginning to the end, I will see D, A, B and C. There is also another way in which you can insert elements into the list, and this is a very typical way of doing it. You will see this in the ADT called list later. So instead of having a list of items and just the list, it's useful to have what is called a head node which has no valid data. So it's going to be a dummy node, and this dummy node is going to point to the list. So we'll call this the head node. It will not have any valid data, and the actual list is only going to start from head.next. And what I want to do is I want to insert a new node here in the beginning of the list, right? So clearly this node cannot be pointed from here. My list should not point to this, because we are assuming that there is always a header node which is dummy, and from the dummy node you should be able to get a list of all the elements. So let's say I have this new node called temp. What I really want is the dummy node should start pointing to temp, and temp should start pointing to A. So now if I want to traverse the list, I start with the dummy node. I will not look at the value in it because I know that it's dummy. I'll go to its next. There is a valid value there, followed by here, here and here. That takes me to the end of the list. So this is a typical implementation of a linked list, where there is always a dummy node, and having the dummy node in place helps you a lot when you do inserts and deletes and so on. You will see this in more detail in a later lecture anyway. So let's look at another method for finding a node. Let's say I have a linked list and I am going to look for a student by a certain name. Then I have to start from the beginning of the list and keep going along till I don't find the student in the list, or the moment I find the student I may want to print details of the student. So I am going to show you a method for finding a node in a list. So remember, my list is pointing to a dummy node called the header node, and the header node is actually pointing to the list. So clearly I should not start searching from the dummy node itself. I should start from the first valid node, which is this. So we'll have a pointer P which points to a node which is past the header node, and we are going to look at one element at a time. If I already reach the node that I wanted or that I was searching for, I can stop and do whatever I want to do with it. Otherwise I have to keep going along, right? Let's see how to write a program for this. So you start with P equals my list dot next or my list arrow next. So what this will do is it will start with P past the first pointer like this. So you start with P, it starts my list dot next, my list arrow next is this field, and that's pointing here. P will also start pointing there. So it starts from there, and the very first data itself could be G, and if it is G, I want to do something about it. If not, I have to go and chase the pointer. I have to move from the first node to the second node and so on. So to do that, we have P equals P arrow next. So we start from here, and if it doesn't satisfy the condition that I am searching for, then I move here and so on. So you have else P equals P dot next. So this takes you one step away, and if you put this whole thing, if this if then else condition, if it's inside a while loop, it will move one element at a time till you either reach the null, which is the end of the list, or when you reach the condition. So you need a while loop around this structure, but this is the basic traversal step. This if and else is the basic traversal step. Now let's look at how to delete a node. So I have this list somewhere, A, B, C is in the middle of my linked list, and header node is here. There are maybe other nodes here and other nodes here, and I want to delete the node containing B, let's say. So one way to do that is as follows. We know that we have to find out where B is pointed to from. So B's predecessor is A, and what I want to do is change the contents of A to point to C as the next element, right? So B's predecessor is A, right? So A's successor should now be C and not B. So what we want is this A's next field, which is now pointing to B, should change to C. This is what we want, right? And we should also delete B in the process, because right now this node is still in memory, and if we don't delete it, it's going to be a problem, right? So we need to be able to delete this also, and this will be reclaimed by the operating system. So let's see how to do that. So you start from the beginning, you keep looking at elements till you reach the node, right? In this case you are reaching B, but you can't go to B and then delete B. So you keep looking for elements whose next pointer satisfies the criteria. So if I keep so if I start from the beginning, I'll keep going along till I hit A, because A satisfies the condition that B is the next node, and this is what I want to delete. So I stop at A and make A's next pointer as A's next to next, right? So A's next is B, its next is C. I take that and I put the value in A. So let's see how to delete the very first node in the list, and I'm going to show you a program segment now. Let's assume for now that the list is non-empty and I have 4 nodes in the list shown in the figure. Maybe there are more elements there, and I want to delete the very first node in the list. If I want to do that, so I start with a variable called temp, which points to mylist.next. So it is this field here, mylist.next is this field here, and I want mylist.next to point to mylist.next to next, right? So mylist.next is now pointing to A, I want that to point to B, right? So that means you actually have this new link that is created, you want that, and temp is still pointing to A is not deleted from memory yet, A is also pointing to B, but A is not in your list anymore. So at this point, if I go and do a search on A, it would be a failure, because it starts with the dummy node, and I'll go past the dummy node, start printing from B, C and D and so on. A is not in the list, right? So however, A is still in memory, you want to remove it. You free temp, which means A is gone, right? So I talked about this in the dynamic memory allocation class. So A is gone. However, temp is still pointing to something which is invalid anymore. So it's not a valid memory location. So you have to make temp equals null. So any further access to temp will be identified by the during runtime. So if you access temp next now after making it null, the runtime when the program is running, this will be an error, and you will have a condition where you are chasing a pointer which is not valid anymore. This will be indicated during runtime. So this is a simple piece of code to delete the very first node in the list. How do we print elements in a linked list? Printing the elements is just traversing the list from past the head node till you reach null. So I assume that the print list is a function which actually takes a pointer to the head node itself, and we want to print out all the nodes except the head node, and I also want to print the number of elements in the list. So display list is this function, or print list. This should have been print list. So we start with 0 elements to begin with. We don't know how many elements are there in the list. We assume that there are 0 elements, and we take current node, this cur node, to point to a node past the head node. So we start with head nodes next. If the list is empty, this ptr to head, its next pointer will be null, so current node will also be null. But even if there is just one element, this ptr to head next pointer will be a valid value, and current node will start with a valid value. So while current node is not equal to null, you print the contents of the current node, move the current node to the next element, and increment the number of elements. You keep doing this in a loop till you hit current node being null, and finally this one prints the number of elements in the list. So you can clearly see how this notion of a loop takes you from one node to the next node to the next node and so on, and this current node is a pointer which keeps moving along, and current node's data will be the data one after the other. So there are several operations that happen on a linked list. So you have create list. You may want to check if a list is empty or not. You want to append to a list. You want to find if a node is there or not. You want to delete a node, maybe print the list, insert at a particular position. There may be several things that you may want to do with the list. So you will see a subset of these things in the class on list later. So there are several things, and you may want to implement these things, and when you do this, you have to be really careful. You have to watch out for a lot of details about how this is implemented and so on, right? So there are lots of things that you have to remember, and it's not good to always leave it to a programmer to go and do this every time. So instead, it may be nice to have the whole thing packaged. So just like what we had for the basic data types like integers and floating point and so on, sometimes it's good to actually package the data that go with the operations that are allowed. So for instance, the moment I say integer, I know that only certain operations are allowed and certain operations are not allowed and so on. So what we are going to do is, I'm going to motivate this in the next lecture, and I will also introduce C++ as a vehicle with which we will do this. And once you have this next lecture on C++, as a very quick introduction, if you notice, the course will now use C++ as a medium of instruction. So this is for all the lectures on data structures. You will see C++ being used. So one reason why we decided to do that with C++ is that the language lets you express the program much more clearly and concisely, and C does not let you do that. So you will see that the course, the lectures on data structures is going to use C++, and it becomes much more cleaner and easily understandable when you use C++. So this brings me to the end of this module. Thank you.